Hi class, welcome back. So we're gonna try another video. Here we're gonna find the horizontal and vertical asymptote where the function is defined using we'll find where the function is defined. In other words, where the domain of the function. We'll find also the holes of the function and the x-intercepts and so on. So let's jump in to this problem. We're gonna first they were asked to find to reduce it. So let's go ahead and reduce this. So I'm gonna say that this is if we reduce it, right? These are not the same functions, right? These behave the same way, but they're not the same functions, right? So so we can see here that these two will cancel each other out. So we would get x plus, oops, let's try this, x plus 1 to the third power and x minus 3 all over to all to the second power. Perfect. All right, so this is the reduced form. Now, it cannot be reduced any further. We do this by counting any common factors. So now we have to find the domain of the function. That is, the function is defined everywhere except at x. That is, x cannot equal. And to do this, what we need to do is go back to the original part of the function. The original function. Look at the original function. And determine where the denominator will be 0, right? Because the original function, that's a 6 square, that the original function looks like this, right? So the original function cannot have this equal 0, right? And cannot have this equal 0, right? Because if it does, if this is 0 and this is 0, then it will make the whole thing, the whole function, undefined, right? So in other words, what I'm trying to say here is to find the domain of this function, we're going to find the values of x where it cannot be, we cannot have the denominator be 0. So that'll be x plus 2 equals 0, or when x minus 3 square is equal to 0. In other words, where the denominator is equal to 0, right? And then we solve for x. So minus 2 minus 2, x equals negative 2. Again, because we have a square here, the only way that this whole thing is going to equal 0 is whenever the inside is 0. So add 3, x equals positive 3. So in other words, x cannot equal negative 2, x cannot equal positive 3, right? Because if it does, that means the function will be undefined for those. So those are the numbers that we're going to exclude from the domain. So the domain of the function is every single number, all real numbers except negative 2 and positive 3. The next one is, let's find the vertical asymptote of the function. If any, determine whether the vertical asymptote is even or odd. So when we look at the vertical asymptote, remember that we're trying to understand the behavior of the function. So the behavior of the function will be the same whether you have the will be clear whenever we actually write it in the simplified form. So we actually want to use the simplified form. So in other words, this is going to be vertical asymptote whenever the denominator is equal to 0, right? So again, we look at the denominator equal to 0. So that would happen when x minus 3 squared equals 0. But we already know that this is going to be equal 0 whenever x equals 3, right? Because we already did that up here. So the vertical asymptote is going to be x equals 3. Now, to determine whether this vertical asymptote is even or odd, all we have to do is look at the power of the factor of that vertical asymptote. So that power happens to be a 2. A 2 is an even number. So therefore, we're going to say this is an even value. And what's important about that is because it will help us understand what kind of the shape of the graph of this one. All right, so let's jump into another one. All right, find the whole. So remember, the whole happens to be the actual value factor that was canceled. So remember that the only factor that was canceled was x plus 2. So this was canceled, so x plus 2 is set equal to 0 and subtracted. That's the whole of the function, right? Now, that's where you will find it. This is at negative 2, but we need to actually find it. So to find it, we need to plug it in back into the function. So please use the one that is simplified, because otherwise you're just going to get 0 over 0 on the other one. Negative 2 plus 1 is negative 1 to the third, and negative 2 minus 3 is negative 5 to the second. That gives us negative 1 over positive 25, right? Negative 1 to the third power is negative 1 times negative 1 times negative 1. And then negative 5 squared is negative 5 times negative 5, which is negative 1 over 25. Hence, the whole is negative 2, negative 1 over 25. Okay, and let's find the x-intercept. Remember what it means to be an x-intercept? It means that it's a point that is crossing the x-axis. So right here, right, somewhere in this line. So that's where y is equal to 0. So your y is 0 at the x-intercept. So x-intercept implies y equals 0. Solve for x. So finding the x where y equals 0. So you take your function, which is x plus 1 to the third, x minus 3 to the second. Remember, we said that these two have the same behavior, so same x-intercept, same y-intercept. So that means we're gonna let y be 0, right, and solve for x. So this is going to be y, so this is going to be y. This is going to be set equal to 0, right, to satisfy this condition. And then we're going to solve for x. To solve for x, the only way that this whole thing is going to equal 0, the only way this is going to equal 0, there's only one way. And that is whenever the numerator is set, when the numerator is actually 0, right? There's nothing the denominator can be. If the numerator is not 0, then the whole thing cannot be 0. So therefore, this translates to a problem of solving for x whenever x plus 1 to the third is equal to 0, which we know would happen whenever when the inside is equal to 0, which happens at x equals negative 1. So that's this is where it's going to happen. To find the actual point, well, we already know that when x equals negative, when y equals 0, your x equals negative 1. So the point is the x-intercept is going to be x equals negative 1, y equals 0. Similar argument for the y-intercept. that's going to happen whenever x is equal to 0, right? If you want to find the y-intercept, you're looking for a point in the graph where it crosses this line, but for that, the x value is going to be x is going to be equal to 0, right? So we're going to solve for y. So whenever x equals 0. So we're going to do the same thing, x equals 0. Wherever you see an x, plug in 0 from the original function. That gives us 1 to the third, negative 3 to the second. That will give us 1 over 9. And so that means that y is equal to 1 over 9. Hence, the y-intercept is going to be 0, 1, 9. Okay, so now let's try the next part. We're going to find the aim behavior of the function. In other words, find the horizontal asymptote. For this, again, we're going to look at the simplified form of the function. In other words, x plus 1 to the third over x plus x minus 3 to the second. Again, the simplified form of the function has the same behavior as the original function. And when we look at that behavior, okay, of course, we're going to try the limit again. But for that, we need to consider simplifying as much as we can, right? But we don't have to simplify to all to some degree, because all we're looking for is the behavior of the function. And the behavior of the function will be determined by the leading coefficients, by the leading coefficient of the numerator and the leading coefficient of the denominator. What I mean by that is the leading term, right? So when you look at the limit of the function, you really only have to look, as x goes to infinity, you only have to look at this leading term times this leading term times this leading term will give us the leading term of x to the third, right? 1x times 1x times 1x is 1 times x cubed. And I'm forgetting to put my limit here. 1 times x to the third. The same idea happens for the denominator. This is going to be 1x times 1x is going to be 1 times x squared, right? We could have had it over here. If you guys think about it, this would have been like something like this. Like that, right? We really don't need to know this part, because the behavior of the function will depend on those two. And now that we have it this way, we can argue that 1 over 1 is going to be 1, and x cubed over x squared is going to be bx. That's all we need to determine the behavior of the function. And again, I forgot my limit as x goes to infinity. And now we can apply the limit. So as x goes to infinity, x is going to go to infinity. And we're going to use the same argument for the other one. As x goes to negative infinity, is going to be the limit as x goes to negative infinity of x times 1, which as x goes to negative infinity, then this is going to go to negative infinity. So they're both going to infinities, right? Negative and positive, so there's no horizontal asymptote. And so let's try to graph this. Here we go. It's already there. So we already have the original function. We already know that we have a y-intercept, an x-intercept. So we have a hole at -2, -1, or 25. We also have a y-intercept at 0, 1 over 9. Let's change that color to purple and solid. There you go. So we can zoom in here, and we can see here that there is a y-intercept at 0, 1 over 9, and there is a hole at -2, -1 over 25. and there's a horizontal asymptote at let's see, where are at sorry, a vertical asymptote at x equals 3. So if I summarize it here like this, we can see the vertical asymptote at x equals positive 3. And